So now we're going to talk about extrema. And you may or may not have heard this term like in pre-calc or math 3, but if we let f be defined on some interval I containing some value c, and there are two things. F of c is the absolute minimum of f on I if f of c is less than or equal to f of x for all x and I. That is just a very fancy way of saying it's the lowest point, right? Absolute minimum means lowest point. And on the AP test, they may say absolute. They also may say global. So just be aware of that. Same thing. And then f of c is the absolute maximum of f on I if f of c is greater than or equal to f of x for all x on that interval. So again, we're just talking about a highest point and a lowest point. You've had relative max and min in other classes, and that was like not necessarily the highest point, but it's where a graph changed from increasing to decreasing or vice versa. So here we're looking at, highest and lowest points. So first graph, here's f of x. What is the interval that we're looking at? This is a closed interval because it contains the endpoints -1 to 2. Is f continuous on this interval? Yes. What's the minimum value? When we ask that, we're asking for the y value. So the lowest value is 1. The maximum value is at the end there, 5. If they ask for the minimum points, then they're asking for the ordered pair. So what, 0, 1, and 2, 5. But if they just say minimum value, that is talking about the y or the f of x. Our second interval is almost the same graph, but it doesn't include the endpoints. So this is called an open interval, and it goes from -1 to 2. Are we continuous on the open interval? Yes, because again, the endpoints are not included, so they're not really holes in the interval. The minimum value is 1. Is there a maximum value? So it's got to be the highest point on the graph, right? And you might want to say something like 4.9 repeating, but remember 4.9 repeating, that's not like a finite number that we can reach. So if your highest point is not defined on the graph, then there is no maximum value. It's supposed to say none. Okay, what about number 3? We have a closed interval. Now, the interval itself, I know the domain isn't defined at 0 here, but the interval that we're looking at that's covered on this graph is -1 to 2. Remember, this is not the same as domain. I'm just saying zoom in on this piece of the function. Is f continuous? No. There's a hole at x equals 0, so x can't equal 0. Is there a minimum value? No, for the same reason there wasn't in number 2. If the minimum value is a hole in the graph, then we don't have an answer, because I could keep including more decimal points. You might say, oh, the minimum value is 0.0001, and then I would say, no, it's I'm sorry, we're getting close to 1, not 0. You might say it's 0.999, and then I'll try not to mess this up. Let's do it one more time. You might say it's 1.0001 because that's just above 1, which is where we are. And I would say, no, it's 1.00001. Or, you can keep adding in zeros. So there is no minimum value. There is a maximum value because our highest point is defined in this graph. So the highest value is 5. Here's a big thing to know. Extrema can occur at endpoints, or they could be at interior points on the interval, like we just had it at this little relative minimum right here. The interior points on the interval would be relative extrema, which we're going to talk more about in a little bit, but relative max or min. If you look at graph 1 and 2, the relative min, where we switched from decreasing to increasing, that was the absolute minimum value. And then, yes, discontinuity can affect the existence of an extremum. That's singular. Extrema is plural. Extremum, max or min on an interval. Okay, the extreme value theorem. If f is continuous on a closed interval a to b, then f has both a minimum and a maximum on the interval. This is just an existence theorem, right? It doesn't tell us what that value is. It just says there has to be one. So if you look at, this is graph 1 described, right? This is a closed interval where the function is completely continuous, so it did have both a minimum and a maximum. Number 2 did not have a maximum because it's not a closed interval. It's an open interval where the endpoints are not defined. And number 3 didn't work out because it is a closed interval, but it was not continuous on that interval. So similar to our absolute extrema, we have relative extrema. So I just wrote that on the previous page. Kind of a similar sort of overcomplicated definition, but it says if there's an open interval containing C on which f of C is a maximum, then f of C is called a relative local maximum of f. Relative and local mean the same thing on the AP test. They'll use one or the other. Just know that they mean the same thing. It's the same as absolute versus global. If there's an open interval containing C on which f of C is a minimum, then f of C is called a relative or local minimum. So all this is saying is we're not talking about the endpoints. So not endpoints, but if you've decided that a value on an interval between the endpoints is a max or a min, then it's got to be a relative max or a min. Relative max or min, remember, it's just where you change from increasing to decreasing or vice versa on a function. All right, so let's take a look at this f of x. This time it says points, meaning my answers should be ordered pairs, at which relative maximum occurs. All right, so we have a relative maximum here at 0, 2. Where's another peak? There's one right here at 5, 3. Is the function differentiable at 5, 3? No, but it doesn't mean that that's not a relative maximum. The definition of relative maximum is that the f of x changes from increasing to decreasing, and it did so right there. Points at which relative minimum occurs. Anytime we're changing from decreasing to increasing. So there's one at positive 3, negative 2. Even though the graph is not differentiable at this sharp turn, it's still a relative minimum at 7, 1/2. So what is the value of a derivative at a relative minimum or a relative maximum? So our nice differentiable places, you should have noticed, those have horizontal tangents. Our not differentiable places were sharp turns. So we could have f prime of x equal to 0, or we could have f prime of x undefined. Draw pictures to illustrate. I kind of did that up there already. Drawing in the horizontal tangents or the sharp turns. Critical numbers. We just got done doing this in pre-calc. Remember in the beginning of the year when you did your inequalities and solving all of those, we had to find critical numbers, plot them on a number line. So here's where it actually applies to something. If f is defined as c, then c is a critical number if f prime of c equals 0. So that would be what we just marked off on our picture. You have a horizontal tangent at c. Or if f prime of c is undefined. This could be sharp turn, or it could be a vertical tangent. I'm not going to write unbounded here because remember, we would want our original f of x is supposed to be continuous if we're talking about relative extrema. So having something unbounded would not be a possibility for an extrema. So let's just practice finding critical numbers. All right, so we just said critical numbers are where the derivative is either equal to 0 or undefined. So the first thing you should do is find the derivative. And then you're going to set it equal to 0, solve. And if possible, set up, or let's do this, not set up. Examine where deriv is undefined. All right, so f prime of x is 2x plus 10. Set that equal to 0. I like to put a note, critical numbers. I'm finding my critical numbers. 0 is equal to 2x plus 10. Subtract 10, divide by 2. I get one critical number. It's negative 5. Will 2x plus 10 ever be undefined? No, this is linear, so f prime x never undefined, but my only critical number is x equals negative 5. We're not doing anything with these yet. We're just finding them. All right, part B. Find f prime of x. So this is going to be 2/3 x to the negative 1/3. So I'm going to put x to the 1/3 down here. Minus 1. I need to set this equal to 0. I like anytime I have a fraction and I'm adding or subtracting something, I like to get it into one fraction. You may or may not find that to be easier, but it would just be making 1 x to the 1/3. 3x to the 1/3. But you know, if I'm setting something equal to 0, I like it to be one fraction equals 0. Okay, so 0 equals 2 minus x to the 1/3 over 3x to the 1/3. I am now finding critical numbers. If that's true, I really only care about the numerator. What makes 2 minus x to the 1/3 equal to 0? Well, that would be if x to the 1/3 equals 2. And if I cube both sides, raise them both to the third power, I get x equals 8. All right. For my next one, when is f prime x undefined? Well, it's undefined when 3x to the 1/3 equals 0. That would only happen when x to the 1/3 equals 0. And when x equals 0. That would be another critical number. All right. For part C. Find f prime of x. 2/3, it's going to be x minus 5 to the negative 1/3, so we might as well put that down here. X minus 5 to the 1/3. Technically, there's a chain rule in here, but the derivative of x minus 5 is 1, so I'm not going to write times 1. But be on the lookout for chain rule. Don't forget about all that stuff. All right, so can f prime x ever equal 0? No, because there's no variable in the numerator, so that's never going to happen. But it can be undefined. F prime x undefined when x equals 5, right? Now, do I have to show all this work and stuff for my critical numbers? No, they're going to be part of a bigger problem. Showing work is good so you don't mess up, but I'm doing this for the notes, writing out like when is it equal to 0 or not equal to. You do get credit for showing that you set parts equal to 0. So, you know, if you don't write this out, I would have shown 3 times x minus 5 to the 1/3 equals 0, and then solved from there. All right, let's see. On part D. Now, you don't want to jump straight into your quotient rule, right? Because you're dividing by a monomial here. What if we just distribute the 9 and then divide each term? So f of x is 9 over x minus 27 over x cubed. I don't love quotient rule, so I'd rather avoid it if I could. So now I can do the derivative with the power rule. So this is going to be negative 9 over x squared plus, let's see, so this was x to the negative 3. 27 times 3 is 81, and it's plus because this was negative 27 times negative 3 over x to the fourth. And, oh, maybe I want to get a common denominator. So that would be like negative 9x squared plus 81 all over x to the fourth. Okay, so I'm going to bring my critical numbers up here. Critical numbers. Can the numerator equal 0? Let's see, we could factor out a negative 9. And that would become x squared minus 9. So when x is plus or minus 3, those are critical numbers. The derivative can equal, it can be undefined, excuse me, when x to the fourth equals, sorry, I should put it equals 0 there. When x to the fourth equals 0, when x equals 0. Now we have to be careful. So far, I haven't run into this problem. All of the original functions are continuous everywhere. But here, the original function is not continuous at 0. So remember, our critical numbers, which help us find relative extrema, they can only be at places where f of x is defined. So even though the derivative is not defined at 0, that's because the original function is not defined at 0. So that's not a critical number because it's not a point on the original graph. It's a vertical asymptote. All right, part E. The derivative is negative 1 over x squared. That will never equal 0 because there's no x up there. The value that would make the denominator 0 is 0, but again, x can't equal 0. That's not in the original domain, so it can't be a critical number. So critical numbers, none. If you think about the 1 over x graph, it's got two branches. One is strictly decreasing, the other is strictly decreasing, and there's a vertical asymptote in the middle, so it never changes from increasing to decreasing. What about a trig one? Let's see. Derivative here. 2 cosine x, chain rule, negative sine x, plus cosine x. I'm going to factor it a bit. Cosine x, if I factor cosine x out, I get 1 from the last term minus 2 sine x. Now, remember last chapter we were like, well, how far do we have to go? The reason I did that is because, remember, you're setting it equal to 0 and solving trig equations like this, which we did in pre-calc, you need it to be in its factored form. This means cosine x could equal 0, or 1 minus 2 sine x could equal 0. We're on the interval 0 to 2 pi. Okay, so we only have to think about one rotation around the unit circle. Where is cosine x equal to 0? At the top and the bottom of the circle when the x coordinates are 0. Pi over 2 and 3 pi over 2. Is the original function defined at those values? Yes, there are no vertical asymptotes for cosine or sine. So both of those are critical numbers. If we isolate sine x, like add it to the right side, 1 equals 2 sine x, 1/2 equals sine x. What are our values for this? When is sine, for what angles is sine equal to 1/2? In quadrant 1, pi over 6. Where else is sine positive? Quadrant 2. What's the pi over 6 angle in quadrant 2? 5 pi over 6. All that fun unit circle stuff we did, it actually still is important, and we're going to use it quite a bit for problems like this. Those are all critical numbers because there are no places at which our function is undefined. Relative extrema, relative max or mins, they can only occur at critical numbers. Sometimes you find a critical number and there is no relative extrema. So here are some examples. Here's a relative maximum, and so the critical number where the derivative gave you 0, that is a relative max. So that's where it works out. Here, I would have a horizontal tangent at C, but that's neither a max nor a min because the graph goes from increasing, flattens out, and then it increases again. So increasing to increasing, no good. Here we have a point at which the derivative would not be defined, but the graph goes from decreasing to increasing. So yes, that is a relative minimum. And something like maybe the cube root of x graph that has a vertical tangent here at the c value at 0. The graph is increasing and then increasing. So even though I found a critical number where the derivative was undefined, it doesn't equate to a relative max or min. So finding critical numbers is only half the battle. All right, so summarizing before we go on. When could a relative max or min occur? When f prime x equals 0 or f prime x is undefined. That's when it could occur. And we could say at critical numbers, if that helps. When could an absolute max or min occur on an open interval? Open interval means this picture here. You're not including the endpoints. Only at relative extrema. Relative max or min. When could an absolute max or min occur on a closed interval? Endpoints included. At endpoints or at relative extrema. It's important. You could have AP free response questions that are just asking you, in part, to find an absolute max or min, and you need to show them that you checked the endpoints and you checked the relative extrema. Okay, finding extrema on a closed interval, so endpoints are included, means that we can now look for absolute maximum and minimum values. So your steps are going to be find critical numbers, evaluate the function at each critical number, evaluate the function at each endpoint, and the least of those values will be the minimum, the highest will be the maximum. Okay, so find the extrema. When it just says find the extrema, you're saying finding the y values. If it said find the points, you'd find x, y points. Find the extrema of this f of x on the interval -1 to 2. So I kind of like to do like candidates here. You don't have to write this, but the candidates. What are the candidates for extrema? We could have endpoints, so f of -1 or f of 2, or any relative max or mins. How do I know where relative max or mins occur? They occur at critical numbers. So let's find the derivative first. I guess I'm kind of going out of order these steps, but I'm going to find the derivative first. 12x to the third minus 12x squared. Set this equal to 0. It's never undefined. Factor it a bit. There are critical numbers at 0 and 1. So other candidates are f of 0 and, squeeze this in, f of 1. Those are all the candidates. Now I need to plug these values into the function and see how they come out. All right, so f of -1, that would be 3, -4 times -1 will be +4, so that's 7. F of 2, 3 times 16 is 48. -4 times 8 is -32. That's 16. F of 0 is 0. F of +1 is 3 minus 4, -1. So there's an absolute minimum value. What's our lowest number? Absolute minimum equals -1. The absolute maximum equals 16. If they said find the x values for which those occur, it would be x equals 1 for the minimum and x equals 2 for the maximum. So just read the problem carefully to see how they want you to answer. Okay, find the extrema of this on the interval -1 to 3. Let's find the derivative. It's 2 minus 3 times 2/3 is 2. and then it will be x to the negative 1/3, so ever over x to the 1/3. F of x is defined everywhere on this interval, but I'm going to simplify this to x to the 1/3 minus 2, all over x to the 1/3. So my critical numbers, when 2x to the 1/3 minus 2 equals 0, x to the 1/3 equals 1, raise both sides to the third, x equals 1. The other possibility is that x to the 1/3 equals 0, x equals 0. So our candidates are the endpoints, f of -1, f of 3, or the critical numbers, f of 1, f of 0. Plug all those values in and see how it shakes out. So -1 becomes -2. Remember, this means cube root of x squared times 3, times -3. So it's going to be -3 times, okay, we're plugging in -1, we're squaring it so it's positive. So -3 times 1. -5. If I plug in 3, I get 6 minus 3 times, now 3 is not going to come out nicely, cube root of 9. That's not a perfect value. Okay, and then let's see, is that going to be positive or negative? 3 times, well, cube root of 8 is 2, right? And this is higher than that. So this is going to be negative something. If we have another negative contender, we'll look further into that. But I know this is more than 3 times 2, which would make this 0. So it's got to be negative. Okay, 1, 2, minus 3, -1. We'll have to come back to our negative something. 0 is 0. Is this more than -5? That's what we need to know. Well, you know what I mean. Is it -6 or whatever? No, because cube root of 9, let's see. How do I say this? So 6 minus 3 times cube root of 8 would be 0, right? Cube root of 9 is going to be 2 point something, but it's not quite going to be 3. So I know that this is going to be -0 point something, because 3 times -2 point something is -6 point something. So 6 minus -6 point something is going to come out less than -1. All I care about, though, is that it's definitely not surpassing -5. So our absolute minimum is equal to -5, and our absolute maximum, the only thing that's not negative, is 0. Okay, last example. Find the extrema. Our candidates, start off with those to change things up, would be f of -50, f of 25. Other candidates would be critical numbers. I'm going to have to product rule this and do a little bit of chain. The first function times the derivative of the second, 1/2, 25 minus x to the -1/2, and chain rule, derivative of 25 minus x is -1, plus 25 minus x to the 1/2 times derivative of x, which is 1. If I clean this up, -1/2 x times 25 minus x to the -1/2 plus 25 minus x to the 1/2. This is where factoring is important. We're going to want to set this equal to 0, right? So we need to factor it out to make life easier. I can factor out, put this down here, a 25 minus x to the -1/2. And if it's equal to, well, no, I won't go that far. No, yeah, if this is going to be equal to 0, no, let's not go that far. Sorry. So if we factor out 25 minus x to the -1/2, we'd be left with -1/2 x. 1/2 minus -1/2 will leave us with plus 25 minus x to the first, so I don't need parentheses around that. I have, in the numerator here, I have -3/2 x plus 25. over square root of 25 minus x. Critical numbers. Critical numbers, the numerator will equal 0 when 3 halves x equals 25. So when x equals 50 over 3, there's one critical number. So that's another candidate. Oh, that'll be fun. And then finally, the denominator when x equals 25. Now, let's double check here. When x equals 25 and 50 over 3, are those in our interval? Yeah, because we go from negative 50 to 25. So just worth double checking there. So we also need to find f of 25. Oh, and I just realized I'm writing that down twice. That's one of the endpoints. So you don't need to find it twice. All right, and the last piece is going to be to check all of these numbers. Now, I'm almost out of time because our actual BC class is about to start, but so I'm going to write down what I got when I plugged things in. You can pause this and kind of check for yourself, but you get negative 50 radical 75. You get, when you plug in 25, you get 0. And 50 over 3, you get 50 over 3 square root of, when you do the subtraction, you get 25 over 3. I don't have to worry about simplifying these because remember, the highest point is the only, the lowest point is the only negative. So here's the absolute min, the negative 50 radical 75, and the absolute max is the only positive value. So, don't get too freaked out if the numbers are getting ugly. Remember, you're looking for the lowest, which in this case is the only negative, and the highest, which in this case is the only positive. All right, that's it for today.